Yeah. All right there. Is that better? Thanks. Yeah, so what I was saying is that I'll just do like 5 minutes prep and then, yeah. Yeah, so basically somebody came in using, I think they're actually from Bitmovin, which is like a big, anyway, don't want to dox anybody, but yeah, anyway, it looks like somebody was using this at work to generate example messages. Hey, yeah, going all right. How are you going? Yeah, just gonna try and just see if this thing. So when this thing hits start, we're gonna actually do the thing for real. This is me. This is the. This is sort of the pre stuff. So an audio channel. Oh, nice. That's cool. Whereabouts? The nomadic life? Descriptor is an array of audio channels, and each audio channel is this. Oh, cool. Awesome. I bet it's nice now, right? Like it's, getting into summer. I know it gets pretty cold around that part of the world. Yeah, awesome. Yeah, that would be cool. Oh, start time. All right. Am I ready though? Let's get the spec up as well. Then we'll actually be good to go. We'll leave that there like that for a bit. In that, like in images with swearing pixels. Yeah, sure. It's all zeros and ones, I guess. There was actually a. Yeah, no. Okay, so. The other week I was at a meetup and, like a video dev meetup, and they were talking about, what was it? Something to do with audio. Basically, it was a way they were doing a way to track latency over like pretty bad links. The idea actually was that you'd have like a sports commentators or whatever other kind of commentator, mainly sports, right? And instead of them being in a studio or being like at the actual site and the thing that they're commenting on, they were seeing whether they could just do it from home or wherever. And so the idea that somebody had was that instead of trying to, like measure the latency using, I think it was like WebRTC. So that's stuff that we've been doing. So that's using stuff like SDP and RTP audio. So yeah, instead of doing it like that, let me get this right. Yeah, okay, I remember now. This guy's a clever guy. He was the one who actually told me about, actually helped me through a lot of my initial like SCTE 35 and other live streaming stuff. Okay, so how it worked is that the people would like load up their browser and, plug in their microphone or even just a built-in mic, depending what they were doing. And the thing is that they couldn't control, like the service provider who's doing this, serving the commentary, they have no idea what devices people are using. So normally in a, like in a live production setting, you've got a whole bunch of stuff set up to make sure these things are okay. Like even me, like I've got a cable running here, I've got Ethernet, I've got like, all sorts of, stuff to make sure it's like, things are okay. If you've got somebody just connecting with a browser, doing live commentary, it's really important to get the latency right, because if somebody's there commenting on something and it's like, oh, wow, what a goal, and the goal happened like 10 seconds ago, it's like, whatever, right? Because they couldn't control the environment at all, basically. One of the things that they did was they actually transmit like this kind of weird, inaudible audio signal. And they use it kind of like a clock. So they knew how out of sync they were based on this inaudible thing. So nobody hears it, but but the receiver, I think, was that how it worked? Yeah. So basically, the receiver would like kind of read this clock and actually be like, oh yeah, okay, like I know sort of how out of sync or in sync we are. So, we're okay to receive this person's commentary or not. So, that's just one of these things that you kind of get nowadays is, I know. I sort of assume it's not some kind of like industry secret. I mean, at least for this company that did this sort of thing, it probably is, to be honest, but whatever. But it's actually pretty cool. So it's just one of these things that these sorts of like live productions need to deal with now, because in the old days, like kind of like what I'm doing now, like I'm just running like a really long HDMI cable along the ground and into some other computer. But imagine if you're doing that over the internet, it's like so it's not so much about getting the latency down, it's about syncing. And that's kind of where things are going, I think. Because just the way IP is designed, it's like decentralized thing, and you've got intermediate hops and all this sort of stuff. Like, the way things are going now, it seems to be they want to be, of course, like keeping latency down where possible, but also like making sure things are in sync is kind of really important. So people are just struggling with different ways to do that sort of thing. So it's kind of interesting. No, I think that's a good, anyway, it is now that's audio, right? But I imagine people do the same things for like actual pixels. Although, of course, as always, video is like just 10,000 times more difficult. Yeah, I think I learned something new too. I've actually forgot about that. The guy asked the question, and because he was like, have you thought about doing like inaudible signaling instead of relying on some software running on somebody's computer? And they were like, oh yeah, like we do actually do that, or somebody experimented with that or something. Yeah, it's kind of weird. Yeah. Okay, so let's get going. So somebody posted an issue to our repo, and they found a bug. Can't believe it! I can't believe there's a bug in this hack job. Yeah, and so basically they found a bug in our SCTE 35 serialization. So what is SCTE 35? I'll just go through again. SCTE 35 is a way of, it's basically like a binary message format, and they use it in live streaming and also in like set-top boxes and even like, you know, old sort of cable and broadcast TV to signal breaks in streams, and also signal. Basically, that's really the best way to put it, I think. It's just to, you know, communicate breaks, pauses, how things resume. You can throw them like directly into MPEG containers and stuff like that. And funnily enough, it's still used today. The main way it's used today is if you're watching this on Twitch or YouTube. I guess you will be watching on either one of those things. But yeah, so when you're watching a video, you know, streaming in particular, at some point, it'll cut and it'll go to some ad. Although I do have ads turned off, at least to the best of my knowledge anyway. But yeah, so like if I had more ads on, I don't know how it works. But yeah, anyway, so yep, you'll go. And then you'll have a cut, and then some other video will load. You know, and you can see a different bar going along or something like that. People have, of course, come up with ways to get around this sort of thing. For the users, they've come up with ways to, like, you know, if you're using like uBlock Origin or whatever, then it'll know and it won't load the video. So the streamers, the corporations and the people who are you know, distributing licensed content, they've used SCTE 35 on the server side to actually stitch videos together. So you're live streaming something, and rather than the player actually restitching things together, they'll use SCTE 35 on the server to actually control encoders and decoders, so that the video is stitched together server side. So what you're getting, what the player is getting, they're just getting one continuous stream of video. So they don't know that there's like an actual ad break coming up. So that's how this thing is used now. It's called server-side ad insertion, which is kind of gross, but you know, hey, commercial world, blah, blah, blah. At least this is open source, so you know, we can all sort of learn about it and learn about new ways to get around it. Anyway, so it's a really old standard, like it's from 1990 something, so 30 years old now, pretty much as old as I am. Sorry, 2001. Okay, there you go. So no, okay, I'm not that young. Anyway, so somebody by the name of JF, Bitmovin is a company that do live streaming. So anyway, yeah, so JF has come in and found a bug in the way that we marshal this audio channel structure. And I believe there's actually 2 bugs that I found. I actually experimented with some AI stuff, which was like super weird. I've never done that before, but anyway, I could actually go into that if people are interested. Yeah. Anyway, so yeah, so I'm hoping that I can just sort of like find it and debug it and write a test so that we know the thing is fixed for the future. This person was using our package, our library, to generate SCTE35 messages to pass to some other system. So they were kind of using our package to test stuff, which, by the way, I don't know, Trav GM, this is something I always think about from our conversations in the past. Yeah, like there are ways to, and I also follow the Zig subreddit and discussions as well. Even if somebody isn't officially, like some company is not officially using some particular programming language or framework, sometimes there are ways to like kind of use it anyway. I know that in my day job, I'm not allowed, like, I know this sounds ridiculous, I'm not allowed to do any programming, right? Like I'm kind of forbidden from writing code and reading it as well in a very weird way. Anyway, but I still can do this stuff because I can write code to test existing systems. And so I actually do this because it's, software and writing code is a really useful way of solving problems and thinking about problems. So, yeah, so it's kind of, every now and then I kind of get motivated to, do this stuff. And it's cool that people can use this even in a sort of non-production environment. So that's cool. Hopefully that inspires other people too, including myself, because all right. So audio channel. Let's see now, we've got this data structure, but how does that fit in with the rest of the message? I can't remember. So let's have a look. Audio channel. Okay, so we've got a splice. Okay, so this is the like top level message. Splice descriptor, I think is the one. Yeah, okay, all right, this is it. Okay, so here's our, like some of the code. I know, I've been seeing some of that stuff, man. I don't know what the hell is going on, but yeah. Oh, at work. Sorry, I missed that. Oh, that's crazy. Okay, I've been looking at your public stuff and I'm like, what? Okay, yeah. That's actually, that's super interesting. Okay, I'll have to reread some of the, anyway. Okay, so here's our sort of top level message when it's like in our own data structure. And you kind of have this top level container, and then within it you have these descriptors, and a command actually is really the one that we're interested in. So if I remember command type, how that works. I can't remember how this works now, but yeah, this is it. Yeah. Okay, so you got this top level message. You got a command, which is kind of like, let's say, the type of message, and then these are the let's call it like the arguments to the command. So this is sort of like the stuff that describes the actual type of command. So, and one of these I think is our audio descriptor. I remember rightly. So audio descriptor. Yeah. Okay. Cool. Yeah. All right. So, oh boy, this is no worries. Yeah. You too. Thanks for dropping by. Thanks for saying hey. And yeah, enjoy the States. Okay. Yeah. So if we look at our splice, this is the one. Okay, so what we're going to do is we're going to find the code that, because the bug is in the serializing the audio descriptor. So we're going to start with look at the code that actually serializes this structure, and I guess we'll find some code that serializes these things. And then eventually we'll get to the code that serializes the audio descriptor structure. That's the one that's the problem. Cool. Okay. Close that for now. All right, Scotty35. Let's just start the formatter. And we'll start the test just because why not? We'll test passing. Okay, well. Oh yeah, they've actually gone here. Splice descriptor.go line 318. Okay. It should be shifted left by 1 bit. Okay, so they've actually found the problem specifically. Set the last remaining bit. Okay, let's go up a bit because we've jumped in right into the audio descriptor. I want to kind of go up and just kind of re-familiarize myself with how this thing works. So let's save that bit there. Let's get another copy of the window. Actually, let's put that there. That here. Audio descriptor, decode all descriptors. Okay, there we go. So, oh no, we're not really decoding. We want splice descriptor. Interface. Yeah, that's right. Yeah. Marshall splice descriptor. Okay, this is a splice structure. And code. Here we go. Whew. I can't believe I wrote all this stuff. Okay, so there's our... Okay, so what's happening, I guess, is... Let's just... I want to have a look at the splice. Let's have the structure in front of me just so I can kind of follow it through, because I guess what's happening is that we'll sort of start, we'll encode each little field. So we're up to tier here. Okay. Let's put another line here because this is just tier. So yeah, that's the timestamp adjustment. Here's the tier. Okay, we're going down to command now. All right, so we're here. All right. And then we go into descriptors. So encode splice descriptor. Okay, and then, so this encodes a splice descriptor. So we just loop through the descriptors. Okay, so should be getting close now. So what this does is if we do doc splice descriptor, yep, data is the encoded splice descriptor implementation. Yep, okay. So we know it's with audio descriptor. So let's look at the data method on audio descriptor, which I guess we sort of had here. So let's just push this here. So we got code splice descriptor. Let's find audio descriptor, right? Okay. Here we are. Okay, so this is, yep. So this is where we were getting at. So there's probably like a, you know, as JF, the person who wrote in with the issue suggested, I'll put that over here. They said, yep. Yeah, these bits should actually be shifted left. 1 bit. So anyway, we'll get to that because we want to write a very specific test, and it should just reveal itself when we write the test. Is serialized wrongly. Num channels and audio descriptor. Okay, so yeah, let's check in the spec. Okay, so let's go to the audio descriptor. I guess is going to be here somewhere. Audio descriptor. Hey, there we go. Whew, okay, it's been a while since I read these specs. I wonder what this actually does. Oh, for example, the signaling of audio language changes. Wow, okay. Interesting, didn't know that. Okay, well, there you go. So it's actually not, yeah, so it's not just like breaks in streams, it's also just changes, I guess is maybe the better term. All right, so let's read through this, okay? So we're gonna have, let's put this over here. Okay, so let's read through this thing just bit by bit, and literally bit by bit. So start with the component tag. Okay, so we're in here. Yeah. Okay, I remember this. Yeah. So you start with the tag, which is just a constant. So it's saying to the, to the person who's going to receive the message, hey, this is an audio descriptor tag. And then we get, okay, descriptor length. Okay, that's saying, hey, there's this many bytes coming up. Identifier, I guess, is this thing. Audio count, okay, so that's telling you how many of these there are. And here's our reserved bits here. So the 4 bits, so we just kind of, okay, let's go. So ISO code. Component tag, okay, so we insert the tag. That's just a single byte. we then append the language. So audio. Oh, audio channel, sorry. Okay, so we need the audio. Huh? Oh, okay, I get it. Right. Okay. So actually, yeah, okay. So what we're doing here is we're looping through each channel of the audio descriptor. So this is like left, right, you know, that's sort of for stereo audio. So let's have a look at audio channel. Yeah, okay, here we go. All right, okay. So what we got is, let's just put this over here. Okay, so here's the structure that we're actually going through here, right? So we've got a tag. Aha, okay, here we go. So this is an array of 3 bytes. So we just, yep, so we grow the, could actually, anyway, yeah. Okay, so we append these 3 bytes to our slice. Here's the thing. And then what they do is they pack these 3, 7, 8 bits into 1 byte. So we've got a bit field here, right? And I guess here's where our problems are. Okay, so what we do here is now we're doing bits instead of bytes. So we're toggling the bit stream mode, which is a 3-bit integer. Okay. Number of channels is a 4-bit integer. Yeah, I think I see what's happening here, right? So we're setting 3 bits, and then we're setting 4 bits, and then we're setting the last bit. But here's the thing. We're setting the wrong bits here. This is what they were saying about shifting left. So if I have a little very bad diagram, okay? So let's go. In fact, maybe I could write a test just to kind of show it. Maybe that would be helpful. But anyway, let's just do the diagram. Okay, so here's our audio channel in binary. So we've got, I'll do, let's do the mode as 3 bits. So that's 1, 2, 3. And then we've got the number of channels. So let's go like 1, 2, 3, 4 bits. And then we've got full service audio. Okay, so let's do like S for service, 1, and just 1 bit. So 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay. Now, what's our code doing? We are setting. We're getting the bitstream mode, which is, we want to get the, yeah. Okay, so we're gonna get the number out of here and then put it to the 3 bits. So shift left 5. 1, 2, 3, 4, 5. Cool. Okay. Now we want to set the next 4 bits. From, what's it from? From the number of channels. Okay, so that's here, the count. And we do it. So we set, but we don't do any shifting. So here's what's actually happening. We're going well, what's happening is we're going like, so this is 0. And then we're going count 2, 3, 4. That's what we're actually doing. And then finally, we're setting the remaining bit. So we're going, so then we get, and then this is the service, right? There we go. There's our bug in like diagram form. Now, yeah. So, yeah. There we go. So yeah, that's a good spotting by JF here. I mean, the fact that they told us, hey, like it's this line, it's like, oh wow, yeah, okay. Now, how are we gonna write a test for this? We know what a correctly encoded audio descriptor looks like. Because I've kind of like just done one, here. So maybe let's do another test. Okay, so I think we're good with this. I might just hide that for now. So let's actually like just write the code that actually tests this stuff. And specifically, let's write a test that actually checks a known good encoded audio descriptor against something that like our code makes. Yeah. Okay, so I'm assuming there's gonna be a splice descriptor, splice test. Okay, cool. Yep. All right. Alrighty. Now, how are we gonna do this? So we know that when you encode the descriptor, it's kind of easy because you just throw in these constants, and then the tricky bit is this actual like this stuff here. So what happens is that if I remember rightly, if we where do we go? We encode. This is here, I think. Was it encode descriptor or something like that? Yeah, encode splice descriptor. Okay, so encode splice. Hey. There. Yeah, so here. So we've got. So given the tag. Yeah, okay. So we do the tag, we start with the tag, we then, let me put it like this. So how we encode a splice descriptor in sort of diagram form is we do the tag plus the length of the data plus the ID plus the actual data, something like that. Oh yeah, and then we do plus for the actual, yeah, okay. But anyway, all intents and purposes, that's how you encode a splice descriptor. And an audio descriptor is a type of a splice, like it's an implementation of the splice descriptor interface in our Go thing. But most importantly is that it has, these, no, not that one. Yeah, actually it's a some variable number of this structure. So those are our bits and bytes. All right. So how are we going to do this? Now, what we really care about checking is the actual, like I said, the data method, which writes out which should be writing out like these. Well, should write out that, but it's writing out something like this. So let's go to our audio descriptor again. Oh, audio channel actually, because we know that's a, yeah, okay. Okay, let's like in our head work out what a good audio descriptor looks like. So let's do something pretty basic. Let's do like yeah. So we're gonna define an audio descriptor, like a literal audio descriptor. So let's go descriptor equals a slice of audio channel. Well, yeah, anyway, okay, so let's do this. Alrighty, so audio channel, what does it look like again? Audio channel, so the component tag is a constant, I think? Oh no. I don't know where that actually comes from. Anyway, let's just do it here, component. Let's just do 0 and then put it to do, because I don't know. Language. Okay, is 3 bytes, and we need a ISO 6392 language. So let's do English. All right. Okay, I guess we'll Google it then. So list. Okay, cool. Wikipedia to the rescue again. English. ENG. Oh, 639-2. Yeah, this is okay. Yeah. Yeah. Okay. Cool. All right. So let's. I mean, we'll just do English because you know that's what we're doing here. So ENG. Okay, makes sense. So is ENG. Okay, bitstream mode. Is a 3-bit integer from that table. Okay, let's do that. Excuse me. Yeah, I should actually just look that up. No. Bitstream mode. Oh no, maybe we can get it from here. Hold on, there's tables. Audio descriptor. Okay, no, it really doesn't tell you. Okay, so search that. Huh. ATSC digital audio standard. I don't even know what this is, by the way, so let's go to the Wikipedia page just because, you know. Dolby Digital. Yeah, right. So it's just a A52. So this is, hold on. A52 AC3. Huh. This is just an audio codec. So it's an audio codec. So it's the bit stream mode of the audio codec. Okay. Even AC3, I do actually, yeah, no, I do. Yeah, I've seen that before. So this is an audio codec, so I guess the famous one is like MP3. Yeah. Okay, so I need to find some kind of bitstream mode that is like a standard one, I guess, would be good to have. So, okay, first up, let's do this. So this is English. Let's find bit stream mode. Okay. .000 is the main audio service. AC3 bitstream modes. Oh, okay. So, oh, hey, at least I can actually look at the spec. That's pretty, I mean, you know, it's hard. So this is one of the annoying things about these, you know, doing this, working with this kind of stuff is that like a lot of these specs are closed. Like you have to pay hundreds of, you know, dollars, euros to access them. So let's close that. What was this? A52. Let's open this one up. Bit of a deep dive. I didn't quite expect this, but anyway. So many committees and stuff. Like, what is this? Bitstream mode. There we go. Okay, so let's just go straight to it. Page 38. Jesus. Okay. Yeah. Cool. Okay, so the karaoke service. No way. What? What? Should we do a karaoke service? Should we say our audio channel is a karaoke channel? That's pretty cool. Look, let's just do 0. Oh wait, this is 3 bits? Huh? Oh, mode is 3 bits. Yeah. There we go. Okay, so let's just do it. So let's just say 0, which is complete main audio service. So this is the complete main audio service. Might do karaoke. Could be fun. Fuck it, let's just do karaoke. So that's going to be 111 in our no, okay, let's just look. The good thing about the the good thing about the karaoke or voiceover also can be is that, like, you know, it's something you can see, right? Whereas zeros are like, oh, like, are they sad? Are they not? You know, you don't know. So yeah, actually doing 111 might actually be good. Anyway, let's just do that for now. Karaoke is 111 is OB 3 4 5 1 2 3. Like that. All right. Number of channels is a 4-bit integer. Yeah, okay, so this is easy, right? So we can just do count as 2. That's stereo. Pretty standard. We could do 1 for mono. Might actually be easier. Let's just do that. Let's do 1. Mono. Full service. That is. We need the, there we go. All right, so this field is a 1-bit field that indicates if this audio service is a full service suitable for presentation, or a partial service which should be combined with another audio service before presentation. Okay, right. So this is like, yeah, okay. So for example, a visually impaired service which contains all elements of the program it should be set to 0 if it only contains a narrative description of the visual program. Yeah, okay, all right. So this is just true. Component tag. Yeah, we haven't looked at that. Okay, let's look at this. Component tag, an optional 8-bit value that identifies the elementary PID stream containing the audio channel. Ooh, yeah, that's actually quite tricky. Okay, that's tricky. If used. Yeah, quite tricky. Right, so the way you actually the way that you set the field is based on some, can be, or should be based on some other value in the message. Stream identifier descriptor. Where's that one again? Anyway, maybe it's not super important, but it should be, if it's not used, it should be all ones, and the stream order shall be inferred from the PMT audio order. Yeah, okay, look, so let's just do like, a bit integer, so wait, what does this thing again? Okay, let's set its OXFF. Reasoning is use the value shall be the same as the value. Oh, sorry, if this is not used, the value shall be, okay. Hey! So let's set this as should be OXFF if not, or if unused. Okay. All right. So we have our, how many bytes is this thing? One. So it's 1, 4. So it's, wait. So audio descriptor is 1, 2, 3, 4, 5. It's 5 bytes. So let's manually write out what we think this should look like. Okay, here we go. So OXFF, well, let's just go. So it's that to start with, and then we want E and G, and then we want, okay, now here's where we do the here's where we got to correctly write this. Okay. So we've done the component tag, we've done the language. Okay, so let's write this out. Component tag. This is the language. And then now we want the last remaining byte. So let's write it as binary. Okay, and then bitstream mode is 0. So we want, okay, so let's look at this. So we want 3 bits 0. 1, 2, 3. And then we want to set these 4 bits, in this case, one. So it should be how many bits? We've got 4 bits. So it's 1, 2, 3, 1. And then the final bit is toggled to 1. And this is yeah, so this is just so count equals 1, full service is true. Okay, so I think now if I almost got it, and not quite, because we need to encode the length and stuff like that. Okay. How are we gonna do this? So we've almost got it. We just need to write the the count is just 1. Hold on. Let's look at the binary representation again. Okay, here's what it looks like. Okay, we're doing these bits. This stuff is handled elsewhere. That's easy code. We already have it tested and everything, so that's fine. it's this here. So the audio count is going to be 1 because we just have one audio channel in our slice. So it's actually going to be like, we can actually write this here. So, but shifted to the left 4. So that's kind of tricky. Yeah. Okay. So we go. Let's just do it like this. OB 1, 2, 1, and then the rightmost 4 bits are reserved. So what does reserved mean? Should they be set to something? Let's check. Oh shit! I think I've. Oh no! I've got that wrong. Sorry, my mistake. Yeah, no, sorry. Hold up, no. Back. So this is on the number of channels. This is the number of audio streams. This is probably the way to describe it. In like the whole thing, the whole sort of like, yeah, in the whole stream, how many audio streams are there? So we can actually just I feel like I'm setting it as the. No, hold on, sorry. Just thinking, number of channels? I feel like this is wrong as well. I feel like I might have stuffed something up here too, because I'm saying that the sorry. Yeah, no, it says here. The value shall be derived when converting to bits from it based on the number of audio channels. Okay, so it is just the number of audio channels. So it's kind of, yes, there's a bit of redundancy, but this is they do this for the binary representation. So it's so you know how many are going to be coming up. Yeah, that's, yeah. So you can allocate memory, that sort of thing. All right, so it is that. So in this case, it is just OB 1, 2, 3, 1, and then reserved, we're going to say is 0. So it's 1, 2, 3, 4. And then what we can do is we can actually turn this into an array rather than a slice, so that we can just do a direct equals comparison. So in Go, you can actually, like say, you can compare byte arrays just using the equals operator. So it's super handy. So you can just go like, if God equals 1, then blah, blah, blah. You can't do that. You can do it with slices, but it's much easier to do it with arrays. And we know what the length of everything should be, so we're fine. We can sort of do stuff manually. So this is just single, we have a single channel above reserved bits untoggled. Right, so we got that, and then 1, 2, 3, 4. Cool. Okay, let's just do that. Okay, so let's do. Let's actually let's encode this thing and see what we've got. Oh yeah, okay, so we need to, audio descriptor, just because we need to convert it to the type that we want, because we've sort of set it like that. And maybe we're gonna get a type slice of, has no audio descriptor of, hey, what? Oh, whoops, yeah, the data, like that. An array of 6 bytes. Okay, 6 bytes. 1, 2, 3, 4. Oh yeah, of course. Okay, so. Okay, hold on. Okay, so got is array of 6 byte. So the serialized, or like sort of marshaled. No, sorry, I always get this mixed up. Marshaled, yeah. Audio descriptor test data. And let me just copy the, as this is kind of one of the ways you can convert from a, well, not convert, but like, you know, you've now allocated 6 bytes and you want to, yeah, you want to copy the value out of this slice. So we go, the destination is, I just figure out how to do this. Right, we're going to do that. Yeah, and then, so we copy the values out of marshaled. Hey, there we go. I reckon that's our bug. Okay. So now the fix apparently is to shift, you know, just based on this little sort of, yeah. So I think, yeah. Let's, okay, sorry. Let's print this out in binary just because then I think we'll be able to see it. I'm hoping we can see this thing here. So I'm hoping we'll see that. So let's go, I remember how to do this. Can I just do that? Wait, yeah, let's just try this and see what it looks like. Can't remember. Yeah. Okay, all right. let's line these bad boys up. Well, that one, and we wanted that. Oh, and then 08B, yeah. So we'll just get some padding. I think we're getting there. Hey, how's it going? Oh, hey. Wow, more people, quickly. Oh, okay. Come at a good time. We're on the home stretch to like actually sort of discovering this, surfacing this bug. So we want let's get this right. So we got that. We want that. Yeah, that's it. No, well, actually, not quite getting there. Not quite. Let me look. Okay. Oh. Congratulations. No, but really, congratulations. Fantastic. Well, yeah, actually, now is a good time to go over it because I'm, yeah, because I'm sort of, I think I've got it, but I don't know if this is, like, I don't understand whether what I think is the fix is the fix. Yeah. So basically, I'll go here. All right, so here's the structure that we're encoding. And what in this? So what's happening is that somebody has was testing or was using our library to test some other system that was decoding SCTE 35 messages, and they found that the messages that we generated, that this library generates, they found a particular field that wasn't encoded correctly. And specifically, it's the a message type of audio descriptor. So if we go back to a, don't really have a picture handy, but if I go to the splice, okay, so these messages signal to players and whatever about changes in a stream, basically. So the common case that we see is, for example, hey, there's about to be an ad coming up, or we're about to like cut the stream, or whatever. One of the commands, somebody is generating a message that's meant to signal something like there's a change in the audio coming up. So for example, there's going to be like a change of the language. So we've got all the stuff that, is kind of like the metadata, and then this is the real meat of the, of the message. So this kind of tells you what type of the, like how exactly the this is where I'm kind of like specifying like when the change is coming. And then this kind of like really describes the actual change in the stream. So there can be more than one. So if we have a look, in our package, we define this as an interface because there's a few different types, but we've got like the audio descriptor, this is a dial tone frequency descriptor. The common one is the splice descriptor. So this is saying, hey, like, there's, the video feed is going to cut or something like that, or get ready to load up some new type of stream. The bug is in the way that we serialize this type of audio descriptor. Why would you indicate audio change? That's a good question. The example that they give in the specification is to do with, like the language is going to change. So now why would you do that? Well, I mean, I remember this is kind of old broadcast stuff. Yeah, so, but in Australia, there's a channel called SBS, and they broadcast like the news in all different kinds of languages. So when I was learning French and stuff, and still learning, yeah, like you can watch the French news. So it kind of, the language changes like quite every hour or something. Yeah, it could also be something like subtitles. Yeah, it could be changing from mono to stereo as well. Yeah, I'm just thinking of other things because the actual type of the change is described in this data structure here. Yeah, so the things you can describe of the audio are the language. You can change the not the actual codec, but the mode of the audio codec. I've just learned this like an hour ago or something, whenever. Yeah, the number of channels, like I just said, you can change from mono to stereo. And then I think, that's just like this indicates whether the audio channel described in, is actually like fully complete, or whether you need like some other audio channel to actually be able to fully understand the whole stream. Something like that. Don't quite understand that. I can't remember what component tag does. The funny thing, so bitstream mode could be like, we're changing from like a complete service to, like we're going to karaoke. So karaoke has its own mode. So if you wanted to communicate that we're going from like, news in English to karaoke in Korean, then this is how you do it. The problem, yes. So the problem is that we are not actually encoding this data structure correctly. And because it's a binary message format, we're not converting some of these fields, or I think it's just one of these fields, to binary correctly. So if I go to here, so this kind of shows you component. So if we have up our own data structure, so we go here. Okay, here's our data structure, and here's like the binary format. So the component tag is just a single byte. The ISO code is like a language, and that's 3 bytes, 8, 16, 24. The bitstream mode is 3 bits. The number of channels is 4 bits, and this full service is just a 1 bit. So what's actually happening here is that we've got 1 byte, 4 bytes, and then they've packed this information just into a single byte. That's that. Wait, so 1, 3, 4. Yeah, so it's 5 bytes. Yeah. Now, and there can be some number of, audio channels. Yeah, and so somebody's found that I can't remember exactly which one, the way that we're packing the bits here, there's a bug. So, yes, and it is the count of channels that we think that is not being packed correctly into this final byte here, 8 bits. So, I've just been writing a test that I think exposes it, and it looks like we have exposed it. Earlier, I kind of did it in my kind of like manually in my head by like drawing a diagram. So how that worked is, for example, this final bit should be, if we look at our, it's these 3 fields that are encoded. So in the final byte, it looks like this. The bit stream mode is 3 bits. So that's mode, mode, mode. Then we've got the count as 4 bits. So that should be 1, 2, 3, 4 bits. And then finally, we've got the full service. So let's just say it's F for full. That's what it should look like. But I think what's happening is, because we're not shifting, it's kind of looking like this. So we're getting the mode, and we're going 1, 2, 3, because we're shifting to the left 5. 1, 2, 3, 4, 5. We're getting the count, but we're not shifting. So what's happening is that we're kind of just, that thing's just left alone there, and we've got 4 bits, so it's 1, 2, 3, 4. But then we're setting the final bit. So what's happening is that we're kind of getting this, and then we're writing, it's actually looking like that. So we're missing a bit. So that's what I think is handling. True. Yeah, that's right. That's true. There is no example of the switch here. I mean, here, so what I've done is here's a actual, so let's say this thing actually says, hey, it's changing to English, and right now we're just using 0 because that's like the default, and mono and full service. So that's like this is sort of that's a complete valid audio channel description. So what I've done is I've gone, okay, I had to kind of look up a whole bunch of things to try and find what the actual valid values are, just making sure that it makes sense in the real world. And here's the bytes manually specified by me, what I think they should be, just based on just manually going through and going, okay, yeah, that's what, yeah, so that's the, and now then, if I actually, so this is what we want, and what we got is actually the result of calling this function, or this method. And then we're comparing them. We're going, okay, did we get the values that we expected? And we actually don't. And so I think that this has exposed the bug. I think, but I don't know for sure yet. I just want to, I'm pretty sure it is though, because no, I think we got it, because this, yeah, because in this case we've got, so it's only this byte that we care about. So that byte is the same as this byte. Yeah, I think, and now I understand. Okay, so yeah, so what's happened is that, and we can actually, it might be easier to see if we use the karaoke mode. What does the output of that test look like? This. So this is actually the an array of 1, 2, 3, 4, 5, 6 bytes, binary. So it looks like we're packing well, yeah, it looks like everything's being like, marshaled into binary, okay, except this final byte, because we got this, but we wanted this. And if I look through, I can see, oh, actually, yeah, this byte is, we want that byte value, but we want, yeah, no, I know, it's all a bit of a mess. yeah, and then, yeah. So, so let's actually use karaoke. I kind of want to put this. Is bitstream mode karaoke. This is literally in the spec. And that is a uint8, and that value is actually 4, 5, 1, 2, 3. That's just usual suspect. Yeah, so let's do that, because that may help us see it more clearly. Yeah, maybe. Okay, let's just line this up. Test isn't that well laid out. We want that. Oh, hey, shit, we found another bug even. Oh no, shifted 3 bits. Oh, the count. Yeah, no. Huh? Oh, sorry, no. This is wrong. No, sorry. Okay, hold up. We want, yeah, it's this final byte. Yeah, see, this bit field stuff is tricky, okay? So, especially in Go, the tooling isn't really there to work with bit fields. And it's actually interesting. I think without a calculator, I do it with pictures. This is, and of course, I do it without a calculator. This is why I get the bugs. This is why the stuff, when I write it, it's full of bugs. That's why. We can see exactly why this came along. All right, so really this should be 1, 2, 3, like that. Let's go creative. So the karaoke mode, so mode equals karaoke. Karaoke. Count is 1 there, and the full service is 1. Yeah, that's it. Okay, so yeah, we've got it. What's happening is that we're actually setting. Yeah, so in our case, what's happening is we're going 1, 1, 1, 0, and then we're putting in the count as 1. Okay, so that's 0, 0, 0, 1. So then, and then when we write in the last bit, that never gets, yeah. So this is 0. It shouldn't be. And that's why we get the 0 there. Okay, so then let's fix it. I know, I get it now. Okay, I get it. It took a while, but I get it. I know now why this person suggested, hey, like should be shifted left by 1 bit. Oh, I explain it again? Yeah, sure, okay. You know what? I think it'll be clearer if I use 2 channels. Oh, no, I can't. Sorry, I can't. Give me a sec. Let me think. Okay, so with the code like this, let me just do final. Uh, 515. I'm going to print out just that byte. And then we'll do okay. Just dump all this. Okay. So this is currently, this is how we encode these fields from the struct. That's this code here. Specifically this. So what's happening is that let's go through the code and do it manually. Okay. We're kind of doing manual debugger. we are the debugger. Okay. So let's now encode this structure manually using this code on the right. So we're gonna so I want to highlight the code that I'm going to be working with. Is this we'll do this here. So this is the stuff that we're working with, the highlighted. Okay, let's see if I get this again, because maybe I misunderstood. All right, so we got the sorry, the fields we're working with are these ones: bitstream mode, count, and full service. Okay, let's go. So we've got a single byte. 1, 2, 3, 4, 5, 6, 7, 8. Wait. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. Here's the counting. These are the counting bits that I... Okay. Bitstream mode. Okay. Bitstream mode karaoke is 3 bits. So we've got 3 bits. So we set that first, but then we shift left 5. So what's happening is that we're going... So in memory, it's actually stored like this, but we're shifting it left 5. So what we're actually getting is... Okay, so we're getting all these ones we set here, and we're shifting it left 5. So we're going 1, 2, 3, 4, 5. Okay. So that's bitstream mode done. Next, this is empty byte. That's the byte that we've allocated there. Okay, now we do the count. So in this case, we are, and what this does is this masks the right 4 bits. Oh no, sorry, because anyway, so I'll just keep going. Okay, so we'll go, let's grab our count. So what is our count? Our count is 1. Okay, so 1 gets written like this, 2, 3, and then we're setting here the 4 right bits. So let's put 1 into these 4 right bits. 1. So 1 in binary is 0, 0, 0, 0, 0, 1. Okay, now we've got, this is our count done. Okay. Final field that we want to set is the full service field. This is just a Boolean here. So let's pack it in. So we're going to have the rightmost bit. Okay, so 1, and then we've got don't touch anything. All we're doing is setting the final bit. Done. So this is full service done. Here's the thing. We've lost our count. Where did count go? Because the spec actually says 3 bits, then, or like 3 bits, and then 2, 3, 4 bits. So the spec actually tells us that the layout should actually look like this. Mode. I'll just, yeah, here we go. So we've got, and then we've got the number, mode, and then we've got the channels as the next 4 bits, 2, 3, 4, and then the full service is 1 bit. So this is what it should look like. But here's the problem. We've set these 4 bits as the number of channels. That's wrong. We want to set these 4 bits. These 4 bits as the number of channels. So what we really want is this. So that's the mode, whatever it is, doesn't matter what it is. 0, 0, 0, 1. And then that. That's how we want to pack the bit. Or like pack the number of channels. But we're not doing that. We're packing these 4 bits. What am I checking to change the 4 bits? Oh, well, I guess like I'm getting that from the spec. It's saying to me, hey, this is how you lay it out. But I'm putting the 4 bits here, which is wrong. I want to put them here. So what I need to do is, okay, here's a big moment. Do you think this is going to work? So I get these, and then I shift it left, 1, like that. And now in theory, this test should just pass. Okay. Yeah. Now, how I work that out is because the thing that I actually want is this. I've written it here. So here's what I think these 6 bytes should look like. Now ignore that first byte because that's from a little bit. That's actually here. You think it's still a problem? Yeah, it could be. I feel like this is a bit weird. I don't know why I'm masking the bits then. Yeah, yeah. Yeah, I think you're right. No, you're right. Nice spotting. There, so threw me off here. No, this still needs to be shifted. Hold on. This still needs to be shifted left. Right? Because we've got, because in memory, right, we've got, like how is the count calculated? Good question. Yeah. So, well, it's actually the number of, I think if I remember, it's, yeah, this is weird, okay? But the count is the number of channels. So this is like mono, stereo, that sort of thing. So this ATSC A52 is the, yeah. So this is passed as a, yeah, it's just a, yeah. Oh, well, actually, I assume so. Let's check. So here's, yeah, I actually opened this earlier to have a look at the, because I didn't know what bitstream mode, like what's even a value. That's a good question. Let's have a look. So table 4.5. Oh, hold on. Let's have a look at this. A52. A4.5 is that in the appendix. A4.5. A4.5. Num channels table. Okay, page 118. Oh. Well, anyway. Okay, I'll do it. I can't remember how to go to a certain page in this. Anyway. 118 was it? Here we go. Here's the bitstream mode stuff. Okay, it's a 4-bit field. No, not at all. Absolutely. Yeah, it looks like a, yeah. But regardless of what it actually represents, the bits, and we still need to shift the bits around, right? So like, you know what I mean? So regardless of what these values actually represent, this is a shifted bits. So for example, let's say, just for sake of argument, let's use like this one. Let's set the number of channels as less than or equal to 6. So 1, 1, 0, 1. So in this case, the count is, yeah, I feel, and you know what? I think I'm going to rename this field, or at least document it that it's kind of, because it's not really, yeah, I think like, now that I read it, audio channel, number of channels is a full integer. Yeah, okay, all right, so let's go here. So let's go OB. So in our case, it's, let's do 1101, okay? So 1, 2, 3, 4, 1101. So less than or equal to 6 channels. So then in this case, okay, so let's do this again. So let's go like, so the bit stream is, bitstream mode we've set as karaoke. Okay, now let's set the audio channel. Sorry, the number of channels according to the yeah, hold on, that mask is weird too, right? Like I didn't. Oh, I know what you mean now, right? I was actually storing. Yeah. I was, yeah, I get it. I was storing it as a byte. Like I should be keeping it as a bit field, not a count. So that, I mean, yeah, I get, see, I get it. Okay. That's another thing with Go, right? What I really want to do is store like 4 bits or 4 booleans or something like that. Yeah. This is another Go thing. It's a bit bit field stuff. They don't really like bit fields. Yeah. So when I hopefully in my unmarshalling code, I do just kind of, you know, it's a 4-bit field. Yeah. So there's that, and there's how can I better represent that? I might be able to, right? If I look at this, maybe there's a way to, you know what I mean? One of the things I could do is actually make a new type. So that's another way that they do it in Go. So for example, you have like type like num channel, num channels or something. And I'm just making it up now. I'm going, okay, yeah. And then you actually just go and, you know, do like your enum. So you go, okay, well, I know 1 is, you know, you say, you know, 1, like, you know, 1 channel or whatever, you know, like, yeah, you know, 1 channel. I'm doing like this. Okay, 1 chan equals, what is it? Over, you know, so, and then you actually just store that as, you know, 4 bits. So you go OB 1, 2, 3, and then 1, 2, 3, 4, and then what are we doing? You know, 2, anyway, right? You just go through and you can you do this as an iota? You could do, right? Because you go 1, it'd be 1, and then you go 1, and then shifted. Yeah. In this case, yeah. The thing is that because I actually never, so in the SCTE spec, I was just like, oh, it's just some value. I don't even know what it is. Like, I'm just going to throw the byte in there and, you know, fingers crossed. I don't know what it is. But now that I actually understand what it is, I can represent it in something, a way that's much more meaningful. So I think I can do it like this. I can do this and then, let me get this right. So plus iota and then shifted. And then shifted iota or something. I can't remember exactly how to do it, but then I can go, 2 chan. Yeah, I'll go 3. How do we do it? 4. So bad. And then reserved. So you just do that. Can you skip? I can do yeah, I think I can. Oh no, because there's nothing afterwards, so I just say reserved and then, yeah. Something like that. And then you know what it really is. Yeah. Yeah, exactly. Exactly. Yeah. Yeah. It's like, woo, we got it. Did for one, yeah. So is this, so okay, so now that we're here, is this going to be, let's change the types around just so we can be like really clear, and then we can kind of turn all these numbers into words, something meaningful. Okay, so the count in this case, we're doing 1101, so this is like 6 chan. Okay, so is 6 chan. This is really, this isn't good, but this is, I wouldn't call it that, but yeah, this isn't, it's not really, I'm not happy with the wording and stuff, but anyway. I don't even know if this in you, like, I don't know if we're really doing the iota correctly here either. Might be right. Okay, so then in this case, we've got mode, channel 2, 3, 4, 1. Okay, so that's what our bit layout should look like. So here it's going to be yeah. Okay, so what's our mode? Karaoke is, don't need a comment there anymore because we're okay. That's karaoke. Our count is 6 chan, yep. Okay, and then let's just make sure. Is that? Yeah, okay. I'm typed in constant overflows. Oh, I've done 6, 7, 8. No, plus iota. Like that. Oh yeah, well that. Yeah, that'll. Okay. Oh, is it just that? Is it, it's that. And a plus iota. And then shifted 1. Hold on. Anyway, let's forget about the iota. Let's just do this manually, right? So we got 1, 2, 3. Oh yeah, it isn't shifted 4. It's shifted bloody yeah. No, it shifted 4, right? Yeah, plus iota, and then the whole thing. I think that's it. Oh. No, okay. Oh, no. No. I suck at this too much. I gotta write it down. Okay, so like that, right? Yeah. Because then we go down, and then we're gonna have on O. Yeah, and then added. Yeah, and then we're adding 1 all the time. I'm not getting. I feel like I'm not missing something here. Anyway, I think maybe I'm just getting tired. 1 and then 1, 1, 0. Oh fuck yeah! Hold up. 1, 0. Yeah, and then 1, 0. 1, 1. 4. And then 1, 1. Is it? Yeah, and then equals. Oh, whoops. Yeah, no, 1 was 0. 0, 1. Four. Yeah. Okay, cool. So now we're going to go here. We're going to turn that into a byte. Okay, deal with that later. Save that. Okay, here we go. All right, so now we'll fix... Let's fix this up to what we expect, okay? So the count in this case is 6, which is these 4 bits. So if we literally copy and paste them, bang, that's what we should get. And the count is, and the full service is true. Okay, so that's what we want. So now let's turn this out. Now we're still stuffing it up, right? This should actually be, we could do a right shift because what we've got the value that we've got in memory is now a byte, and it looks like this. We've got we've got that in memory. So what we really want to do is actually shift that right 3 positions. Yeah. There we go. Yeah. Because, yeah. So let's look at this diagram here. We've got a thing in memory, and it still looks like a number. Well, I mean, it's sort of, it's like a big Indian, blah, 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 yeah. So it's mode. The thing we've got in memory is, we've got this in memory. We've got 6 channels. So it's 1, 1, 0, 1, and then 1, 2, 3, 4. So we want to put these 4 bits into here. So we shift this to the right 3 bits, and then we just, we shift that 1, 2, 3. Yeah, that's it. Yeah, shift it to the right 3 bits, and then we copy it in. Yeah, that's it. Yeah. Yeah, it's weird. It's like just shifted, like they just go. So it's really like, the logic is, you toggle. Is that it? Yeah, I know. This is the stuff that. Yeah. Okay. Yeah. All right. Yeah. Yeah. So, yeah. So what this says is, yeah. So it really does need to be its own, like its own type or something like that, just to represent it. This is reserved. Yeah, that's it. Okay, so, and a little bit, yeah, this kind of, I mean, yeah, it looks weird, but actually it kind of, so what this is that this is just incrementing by 1 all the time. So this is plus, so another way to write this would be 1, 2, 3, 1, 2, 3, 4, and then plus, you know, 1 shifted 4, and then you start going down, or up rather. So then this is 2. Yeah. That's, and this is the actual, yeah, like that. And then, yeah. Yeah, that's the, that's what it looks like. But you can just omit that and just have it all like that. Because that's what it looks like. So you got this number, and then you shift, and then you get 5, and you shift it 4. So and that kind of shows you how they, I guess it kind of shows you how they, like, the whatever this standard is, like that's how they came up with the values. Now, this is num channels, right? But actually, you know, like this even could be its own little package, right? I mean, no, I'm not going to do that, but, you know, because this is actually about the AC3 audio codec. So these values actually have nothing to do with SCTE. So you could almost just have like your own little, you know, package that deals with AC3, and then actually have, you know, something like this is the AC3.mode. And this is an AC3 channel, like number of channels or channel count. Then that will be very clear. You write tests, you know, yeah, that would actually be quite, you know, I don't know whether I really want to go into the AC3 codec, but it's a not bad way of representing it, you know. Because this bitstream mode isn't, you know, there's a whole bunch of them where I got it from, but yeah, like there's all these like silly things, like, you know, well, not silly, but there's karaoke, and then there's like I can't remember now. It was a page. If I can remember the page. Yeah, this is the one. Yeah, here we go. See, dialogue, commentary. Actually have those values and then sort of give meaning to the whole thing. Then you don't have to worry about like all this, you know. Yeah, I actually kind of like the idea of doing that, to be honest. Because I've seen that already. Right? I've seen this type of thing already. I've seen other packages. I've seen other code out there kind of get things quite mixed up. Exactly like what I've done here. Well, no, not like that. But for example, there was an HLS package in Go, like a Go HLS package, and it like tried to deal with SCTE 35 messages, but it was just like a bunch of base 64 encoded. Like you didn't even know what it was. Whereas in our library, what we do is, if you have a look at our HLS package, M3U8, the actual file format, but yeah, we go to date range, I think. Yeah, okay. So there's a type of, so if you look at an HLS playlist, which is just lines of text, you have these little tags in there. So one line, a line can either be like a file that you download or some kind of metadata. So there's this kind of tag. And in here, what we do is we just have pointers to these structures. So you don't have to know or care how, like, what the hell this stuff even, like how it's encoded or anything like that. You just give it the structure that's sort of, defined. And then the package kind of deals with it all for you rather than you needing to like pass around strings everywhere. Or in this case, we're like passing bytes around. It's like, oh, there's UN8. Well, what's that? Well, fuck if I know. Yeah, so, yeah, that's actually, I might actually just put that as like a little to-do, or maybe even just make a little thing here. And then it's going to be like, blah, 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 AC3 audio codec. Good, I'll just write that there for now. Something for later. Okay, so let's get this right. Right. And then we want to set the here we go. Let's do it. I think it's clearer to actually do set bits 0 to 2, and this is set bits 3 to 7, and this is set last bit. I think that's clearer. Don't have the weird mask in there. Very, very, very good spotting by Ringo Ma. Oh, hey. Yeah, and regular expression. Nah, very, very good spotting. Yeah, would have been a long time before I found that. Yeah. Really good. Very good. So let's do this. So let's just write this down here. So I want to put out like a bit layout or something like that. So, it's freezing. I don't know what the actual temperature is. I think it says it's 20 degrees here. In this room, I mean. Okay, so we've got the next 4 bits in here are the num channels. So num chan. And then full service. Now I understand why they have... Oh, I get it now. I get it. Okay. This is why they kind of a little bit of redundancy in the message. So you start with this now makes sense. Because in the whole, not in the channel, but in the descriptor, right, which itself is just a slice of audio channels, right? You actually, let me get the diagram that's much clearer. No? You have that field, this field, and then a count, audio count, which kind of tells you how many are here. But that doesn't necessarily tell you, that doesn't necessarily correspond to the number of channels. Because the number of channels, as we've seen, is like it's like less than or equal to 6. So now I've written 6chan, 5chan. I mean, that's really terrible, but whatever. Certainly way clearer than before. Yeah, like you because at least reading from this other spec, which now is page 118. Yeah. So this can be 5 or less, or 6 or fewer channels. So I get it now. So now, and also when you're dealing with binary, you need to have like a length field before you have like some data, so that you know like how much memory to allocate and when to stop and all that sort of thing. So there's also that. But I kind of understand it a bit more now. Before I didn't really get that. Whew. All right. So yeah, shit. Now, the other thing is that we're not, when we store audio channel. Now, oh, look, we don't even have code to unmarshal it. So given binary, we don't have a way to read in the audio channel data. Just don't have the code. So that's another thing. So if we look in here, like it'll be like, decode descriptor or something like that. Encode splice descriptor, okay. Let's have a look at the Go doc. So we have an audio descriptor. A splice descriptor is the one. Decode. What? Oh, okay, yeah, all right. So decode all. Here we go. Look. Okay. Oh, well, look, hey, at least we're returning an error. So what happens is that we, given that byte slice, hold up, where's my, oh, fuck's sake. Okay, so when we start decoding these, or like decoding bytes, and then we're filling in this descriptors field, then we actually error out if we see something that we don't support. So right now we only have, what is it? Time switch tag. Look at that tag. Yeah, here we go. There we go. See, there's our tag audio. See? So there we go. So we don't actually have the, yeah. So what do we actually support? Tag avail, tag segmentation, DTMF, not time or audio. Okay. That's I mean, okay, whatever. Like, we just haven't written the code, so, you know. But that's fine. Okay, well, look, I mean, shit. Okay, that actually worked out way better than I thought. I mean, I was sort of thinking that we'd just, you know, like shift left by 1 and sort of be done with it, but it was definitely not that. But it's good. Like, that was like, I actually learned quite a lot. I'm feeling pretty happy about that. So yeah. That's good stuff. Okay, so let's actually commit this thing, because I'm sort of happy with that bit packing logic now. Hey, listen, that was a great catch, by the way. That bit masking stuff. It was like, yeah. And then how you were saying, like, are you sure this is like really a count? It's like, well, no, it wasn't actually, really, was it? I mean, it is and it isn't. Yeah, no, it was yeah. No, that was great. Okay, so let's what do we got here? 50 lines of code at 45, so. I have a heater. Yeah, I have a heater plugged in somewhere, but I don't quite need it. I'm wearing a few layers, so I feel okay. I'm a little bit cold, but it's okay. All right. Stage this. Oh, problem here. That is not what we want. That's in splice test. No, here's the thing. No, I need the sunglasses during winter, because the sun, like, you can't, and yeah, look, the problem is that I don't have the sun, this screen, this display, this monitor is polarized, and the only sunglasses I have are polarized. So I have to close the blinds here, so it gets a bit cold because the sun doesn't come in. So in winter, the sun is lower and it comes in through the window, like right there. Like, actually I can, yeah. So I actually really need to get sunglasses, because I also like, for my day job, I work here, and it's nicer to just have the sun in, because, you know, my heater is like really small and shit. So alrighty, okay. the audio okay, first, so serially masking bits. In the audio descriptor in an audio descriptor. Okay. And this actually resolves, what are we at? 39. I'll just do the thing that's easier. I like that because format that, like that. Okay, whew, all that for 45 lines. Cool. Okay, well, with that, I'm just thinking whether to take a break, or I do need to have lunch and all that because it's 3 p.m. here. So, so I'll probably cut it there. Definitely upload this to YouTube because this was actually a really good one. Yeah. So thanks again for the help. And yeah, hopefully this inspires people to do stuff. Yeah, but thanks again. So yeah, it was, and it was actually, yeah, like, I mean, the fact that I even went into this AC3 media, audio codec thing, I was like, oh wow, yeah, dual mono. Great lessons we get to learn here. Yeah. Yeah. Definitely a good catch by whoever found the bug, JF Bitmovin on GitHub. So yeah. Cool. Okay. Thanks. And see you next time, hopefully before too long. Yeah, day job. Blech. Okay. Thanks, everybody. Cheers. Bye. I'll do this. Yeah. Okay.